Welcome back, ladies and gentlemen. Today we're going to tackle section 12.2, the area of right prisms. Up on the screen, you'll see your exit question for the day, as always, and we'll jump right into it here today. First, I want to remind you of some vocabulary words that you learned last session, but they're going to come into play here because you're going to be asked to find the area of various bits and pieces of a polyhedron. So just to remind you, vertex, face, base, and edge. To that, we're going to add little descriptors that are a little more specific. So you have the base of a polyhedron, but in a prism, there are also lateral faces and lateral edges. Those are the pieces that are not a part of the base. So the lateral faces would be the non-base faces, and the lateral edges would be the edges of the polyhedron that are not part of the base. Also, a couple more descriptors: right prism versus oblique prism. Right prism, the faces are normal or perpendicular in every way to the base, and an oblique prism is not. Notice that though still in the oblique prism that the faces are parallel to each other, or the edges are parallel in the oblique prism. The big concept today is that of a net. A net, and it's also a vocab word, so I'm sure there's a spot for it on your note guide, is a two-dimensional representation of a three-dimensional object, or the surface of a three-dimensional object. So one, write down that vocab word, and then secondly, see if you can unfurl or cut apart and lay flat as if it were like a two-dimensional object, this rectangular prism that I have laid out. Pause the video and see if you can draw a picture. If you've done that correctly, it looks a little bit like this. So you can go either way. You can take a three-dimensional solid and unfurl it and get a net, or you can take a net and fold it up and get a polyhedron. And as you can expect, it's not going to be as simple as just rectangular prisms all day long. You're going to be basically expected to find, or to at least figure out what the net is of any closed figure that you can imagine. So for example, down below there's a square pyramid shown to you. And the big one for today is what the net of a cylinder looks like. So see if you can pause the video and draw the net of a cylinder. If you do that correctly, you have, think of like a tin can, unwrapping a tin can. So you cut the lid off the can and you cut out the bottom off the can, and then you have the label of the can. And then more importantly, the net of any shape allows us to then calculate the surface area of that shape. So another question along with this net of a cylinder is, how would you find the area of the outside of the cylinder, or the surface area of the cylinder? And you might say, okay, well, it's got a circle and a circle, so that means that I can find the area of a circle, which is pi r squared, and another one, pi r squared, so you've got 2 pi r squared there. And then you have to figure out how big this label is. And it should be pretty obvious that the height of this it's a nice clean rectangle, so it's just length times width, or height in this case, and that height corresponds to the height of the cylinder. But then think about how long this is and where did that length come from. If you examine it a little bit closer, this edge right here was wrapped around the bottom of the can. So that would be the distance around the circle, or in other words, the circumference. So this distance right here is 2 pi r, or pi times diameter, whichever circumference formula you like better. Which brings us to our formula, or our theorem for the day, which includes a formula, and it has two versions of it. One that's very general. It says the surface area of a right prism, so it does have to be a right prism, is 2 times the area of the base plus the perimeter times the height of the prism. Now I want to point out that I'm going to use a capital H to signify that I'm talking about the height of the prism, and I'm going to use a little h to signify that I'm using, like, say, a height within a triangle of a prism or a pyramid. So the height of the triangle or trapezoid that's within the prism, I'm going to use a little h for, and a capital H I'm going to use for the height of the three-dimensional figure as a whole. Another way to say that is, well, I guess, again, if you're using a polygon, so this is 2 bases, and remember we had that 1/2 apothem times perimeter thing? Well, that's the area of a polygonal base of some sort, except you have 2 of them, so the half coefficient gets eliminated, and then the rest of it is the same. However, even though this is a nice, neat little formula, and in some cases it can be an excellent shortcut for you, my suggestion is basically just draw the net and figure it out. Draw the net, see what shapes you have that you're dealing with, and try to find the area of each shape. Oftentimes there'll be a shape repeated, so it's super easy, but I think that's the best way to do it, because rather than memorizing a whole bunch of different formulas, that always seems to work for me. Speaking of, let's talk about that cylinder a little bit more, and we kind of talked about it, but what is the exact area for the surface area of a cylinder? Well, we have two circles, 2 pi r squared, and we have a rectangle with a height of whatever the height of the cylinder was and a length of whatever the circumference of the circle was. So if we start with the formula from theorem 12.2, we have 2 times the area of the base, so 2 times pi r, plus the perimeter, which would be circumference, times the height of the cylinder again, which would give you that. And that one's worth writing down because we talk a lot about cylinders here, and you're going to use that over and over and over again. So to start off, I actually want to do an example, and I just would like you to find the surface area of a regular decagonal right prism. We're going to assume that's a right prism, even though it's not in the description. And to do that, we're going to take our formula. We're just going to start off with our formula and see what it tells us to do. So I'm going to use the formula this time rather than just drawing a net. You can go ahead and draw a net, but you're going to get to the same place that I just got to right here. So this formula says take 2 times the area of the base, so 2 times the area of this decagon, plus the perimeter of the decagon times the height of the prism. We only have one of those numbers, the height of the prism. So we're going to have to draw one of the bases and label what we know and see what we can figure out. So the area of this base, we're going to use the formula from the area of a regular polygon, which would be 0.5 times the length of the apothem times the perimeter, which means I need a length of an apothem, and I need the perimeter too, so I need the length of an edge. So to do that, I'm going to draw a triangle in there to help me. I'm going to draw a triangle that uses the edge of the decagon as a chord of a circle, and that kind of thinking of that as a radius. And then I'm going to split that or bisect that angle right there to get this smaller triangle, this smaller right triangle, because right triangles are handy to have, and it has an apothem on it. So from there, I need one more piece of information, and from our work in 2 dimensions, you probably know that we need to find this angle right here so that we can talk about the even smaller angle inside that smaller right triangle. So it is lucky that we have a regular decagon in this shape, so that means that we have 10 sides, and if we take 360 degrees divided by 10, we get 36 degrees, and that 36 degrees would correspond to the large angle that encompasses the whole side. Chop that in half to get 18 degrees for the smaller angle in both of these smaller right triangles. And from there, we can figure out what the length of B is and what the length of A is. B is going to help us figure out perimeter. The apothem is going to help us figure out the area of the base. So see if you can write 2 trig ratios to figure out the length of A and the length of B. If you do that correctly, you get these 2 equations. You can solve those equations very easily by multiplying by 12, and you get those values for A and B. So we have our length of apothem, but we don't have our perimeter yet. So that's what I'd like to work on next. We do have a value for B. B is 1/20th of the perimeter because it's half of one side and there are 10 sides. So we would take 20 times the value of B, and if you do that, you get 74.2. And from there, we have all of our numbers. So we just pop them in, substitute in each number that we have, and punch it into the calculator, and you'll get 2,776 meters squared. Always add a label. And we are surface area, so we do have to do square units, not cubic units. Next up, we have a pretty awesome problem, and this is a Campbell's soup can, and I would like to know the surface area, the exact surface area, in fact, of the label. And we are told that the total height of the can is 14 centimeters, and the total surface area of the entire can is 144 pi square centimeters. But there's a little problem because there's a little bit of a lip on the can that cuts into the surface area of the label. And I want to figure out what the surface area of this label is. So The first thing we have to do is figure out where that surface area for that label is, or what shape that label is. And you have to kind of remember back to unfurling a cylinder, which would be two circles, the top and the bottom of the can in this case, plus the label. And the label will be the circumference of the circle times how tall the cylinder is, but unfortunately it is going to be slightly smaller than whatever they gave this number for. So it's going to be 0.5 centimeters smaller than 14, so 13.5. However, that surface area covers the whole thing, so we need to figure that out. Anyway, to figure out the area of this label, we need to know how tall the cylinder is, 13.5, with that little modification done for the label. But we also need to know how long it is, so we need 2 pi and r. And you notice they didn't give us a radius or a diameter, so that's something that we need to figure out. As you suspect, that's probably going to involve using the last piece of information that they gave us, which is the fact that the surface area of the whole can is 144 pi centimeters squared. So let's start off with the formula for a surface area of a cylinder, which looks like that, and plug in everything we know, which isn't much in this case. We know the height and we know the surface area. So we know the total surface area for the whole can is 144 pi, and we know the height of the overall can is 14 centimeters. From there, we have to solve this for r to figure out our radius. And this is the point at which you're kind of freaking out, saying, how am I going to deal with that pi? Especially given the fact that in the end, we want an exact answer. So that means that we can't really just convert it to a decimal and hope for the best. We have to keep that pi in there the whole time so that we have an exact answer at the end of our problem. So first thing to do is to combine any like terms here, and you'll notice we have 144 times pi, and we have a number times pi times an r squared, and then a number times pi times r. So these three terms that appear are actually all not like terms, so we can't combine any of them. However, this is all multiplication here. So we have 2 times pi, which I'm going to keep, and then I have 2 times pi times r times 14. So the 14 and the 2, multiplication can happen in any order. So I can simply take that 2 times that 14 to clean things up. Let's try that. Starting to look a little better at least. But you can start to see now that this is basically a trinomial, because I have like a number times x squared plus a number times x, and then a number without a variable attached to it at all. So let's set this up as a trinomial, moving that 144 pi over to the right hand side of the equation. And then it's starting to look like something that maybe you might want to try factoring. Well, the first rule of factoring is that you want to remove a GCF if you can. So you look at all of these terms and try to figure out, is there a number that I can divide all of these terms by? And they're all even. So you have a 2, a 28, a 144, and they all have pi in them. So you can divide both sides of the equation by 2 and a pi. If we were doing an expression, you could factor out a 2 pi, but since this is an equation, we can just simply divide both sides of the equation by 2 pi. 2 pi is a number, it's like 6.28-ish. And if you take 0 divided by that, you get 0. And if you divide all of these by 2 pi, well, the 2's cancel and the pi's cancel, basically. And it reduces the size of the coefficients down to something that's manageable and totally factorable. Factor that up, you get solutions of negative 18 or 4. Obviously, the negative 18 doesn't make any sense, so you're just going to use the 4. And then we have to think, okay, we did all that work for a radius, and we eventually want the area of this rectangle here. So we have 2 and a pi, that's fine. We need our radius, we got it, and we need our height. And remember, our height this time is going to be a half a centimeter shorter because there's a quarter of a centimeter on both sides. So we're going to use 13.5 there. So the surface area of the label, 2 pi r times the height of the whole can minus 0.5 centimeters, which was 14. And then giving this as an exact answer is just our next problem. And basically just follow order of operations. You can do subtraction and then multiplication in any order. So you basically take 2 times 4 times 13.5 and put that in front of the pi. And so it looks like 108 pi square centimeters. So that's kind of like 108x square centimeters. But that's your answer and you're done. There's your assignment for the next day. I'll see you next time.